All right, how's it going, everybody? So this is going to be the walkthrough video for our lab on exploring the gas laws. So I'm gonna be doing this in Google Docs, but you can do this in Excel if you want to. They should pretty much function the same. Most of the things you can do in Excel, you can do in Google Docs, but I'm going to be using Google Docs because that is a free spreadsheet that everyone should have access to. You may need a Gmail account in order to open up a Google Docs spreadsheet. But if you just Google Docs and then go to spreadsheets, or maybe Google Docs spreadsheet, and just open up a blank spreadsheet, you should get to this a page that looks like this right now. All right, now this is going to be our spreadsheet analyzing the data taken for exploring gas laws. So I'm going to change the title up here into gas laws. And it might be a good idea for you to just write your name. So I'll write my name, David Sicilian. And just click out of that, and that should save. And the first thing we want to do is import our data from the video. So you should have watched the video by now, and you should see that pressure versus volume data was taken for a sample of air. So I'm going to go ahead and copy in that data. And before doing that, let's make some headers for our columns here. So the first column will be volume of our sample, and that's in milliliters. And the second column will be pressure, and that is in kilopascals. Okay, I'm going to just pause the video, copy in that data, and then restart the recording. Okay, so now I've copied in the data, and you can go ahead and just pause the video right here and copy this data in as well. And so what we should be seeing here is that as the volume increases, as we expand the chamber our sealed chamber with the gas, we should see the pressure go down, and we do see that. But what we want to test is, does this follow the exact relationship as given by the ideal gas law? Okay, so the ideal gas law is, as you might recall, it is that sorry, let me get the pen working here. The ideal gas law says that the pressure times the volume for a sample of gas is equal to the number of moles times the universal gas constant times the temperature of the gas sample. And so we are trying to study the pressure versus volume relationship here. So if I rewrite this equation, I get P is equal to, I'll kind of group these quantities together, nRT times 1 over the volume. Okay, so I took this equation and I divided both sides by volume. So what our relationship should kind of look like if we were to plot pressure versus volume is sort of like the equation y equals 1 over x. Or you could think of it as really that equation scaled by some constant. So y equals maybe c times 1 over x. So let's see what that looks like. So if we go to desmos.com, they have a beautiful free graphing calculator. And this should be what their homepage looks like. If you click on graphing calculator here, that will bring us to their graphing calculator. Now if we input y equals 1 over x, we get a relationship that looks like this. And so this should be what our data looks like if, let's say, y was our pressure, so pressure on the y-axis, and x is our volume, so volume on the x-axis here. What we should see is that as the pressure gets really, really super high, that the volume, approaches zero. So as the pressure approaches infinity, the volume approaches zero. And, intuitively what that means is if you were to compress a gas sample, just increasing that pressure higher and higher and higher, you should see the volume go down to 0. On the other hand, if you took your gas sample and expanded it to larger and larger and larger volumes, you should see that the pressure of that gas sample approaches 0. So if you were to take some quantity of gas and then expand the chamber that it's in to an infinitely large volume, then there's so few gas molecules bouncing around that they should basically exert 0 pressure on their surroundings. And so I'm just trying to give an intuitive explanation for this type of relationship here. Let's say, if you increase the pressure increase the volume to infinity, that you should see that the pressure goes down to 0. And vice versa. If you were to increase the pressure to infinity, you should see that the volume approaches 0 here. And we don't need to pay attention to negative values here. There's no, I don't know how to make sense of a negative volume or, say, a negative pressure. So we're just interested in the positive values of this relationship here. So let's go back to our spreadsheet and see if our data gives us this type of relationship. Okay, so what we want to do is make a scatter plot and see if the pressure versus volume relationship is as the ideal gas law would predict. So what you do is you go up into Insert up here and click on Chart. Now I'm going to make this a lot smaller to kind of get it out of my way here. So I'm going to minimize my chart. Right now it has no data in it. But you should see this chart editor pop up. Now under chart type, we want this, so click on the drop down menu on chart type and find scatter. So we want this to be a scatter chart. Under data range, it has the cell that I had highlighted in there. Go ahead and delete that. But under data range, once you've clicked in there, you should see this button right here for select a data range. So click on that, and with the cursor in here blinking, select the pressure column. So click and drag over that pressure column and then just hit OK. And then under x-axis, so click into this for add x-axis. And again, so once you click that, you should see this button for select a data range. And then click into there, and then click and drag over the volume data. Okay, and so it does look like that relationship we were kind of expecting. It's hard to tell exactly without fitting some sort of trend line. Maybe we could fit that type of equation to it to see if it fits our data really well or not. Unfortunately, Google Docs does not offer this type of trend line to fit to your data. So we can't try to fit a trend line to this data. So the last thing I'm going to do with this chart is just let's give it a title. So go to Customize and click on Chart and Axis Titles. And under Chart Title, let's just write pressure versus volume. Okay, and then you should just be able to get out of the chart editor, and we have that. Okay. So it does look kind of like what we expect, but how can we be more sure? Well, here's what we can do. So instead of plotting the pressure versus volume, what we can do is we can plot the pressure versus 1 over the volume. And I'll explain this here in a second. So I'm going to make a column 1 over volume. This will have units of milliliters to the -1, so the inverse milliliters. And let's go back to our notepad here. So back to the ideal gas law. What this kind of shows here is that if we were to actually plot pressure versus 1 over volume, so if 1 over volume is a thing, then what we should see is a linear relationship. So let's rewrite this as P equals nRT, all this stuff, times V inverse, or 1 over volume. So pressure versus 1 over volume is just a constant times 1 over volume. So if we were to plot the pressure versus 1 over volume, what we should see is a straight line. And if that is the case, then this law is being followed. So let's try that now. Okay, so back to our spreadsheet. Instead of having volume, what we want to have is the inverse volume, or 1 divided by the volume. So let's click into this cell right here and hit equals, and then 1, and then the divided by symbol, and then you can just use your mouse to click on our volume cell. And then you should just be able to hit enter. And that calculated the 1 divided by 10. Now we can go to the bottom right corner of this cell with this cell highlighted, and once the cursor kind of changes forms and turns into that, you can click and drag, and it will do that for the rest of the volume measurements. So we have 1 divided by 20, 1 divided by 30, 1 divided by 40, and 1 divided by 0.02. Now let's see that if we plot pressure on the y-axis versus 1 over volume, let's see if we do get a linear relationship there. So let's make another chart. Let's go to Insert Chart. And let's see, we want to change the type to a scatter. Oh, and let me make this a lot smaller so I can kind of get it out of my way. And then in data range, let's delete that H2 and click on this Select Data Range. Again, I'm going to select the pressure column and hit OK. And then under X-axis, click on that, and then click this button again for Select Data Range. Click into there. Now I'm going to click and drag on the 1 over volume column. And so once you do that, your data should show up on your chart. Let's go ahead and customize. Go to Customize and Chart and Axis Titles. And let's give this the title of Pressure versus 1 over volume, or inverse volume. Okay, and then just exit out of that chart editor. Okay, that looks fairly linear. Let's try adding a trend line to it to see how well it fits the data. So if you click on the data and then right click, let's see, you should be able to right click and then do, did I forget how to do this? Let's see, click the data, right click. I'm not seeing trend line. Okay, I'm going to pause the recording 1 second. Okay, so in order to get our linear best fit here, what you can do is just double click on the on your plot again, and go down to go to Customize, and oh wait, I'm sorry, go to Setup, and hang on a second. Okay, I'm sorry, what you actually want to do is not double click on the chart, but double click on the data. So double click on one of the data points, and this should pop up. And under Series, if you scroll down, you should see something that says Trend Line. So click on that. It's already the correct type, it's linear. And then under Label, click Use Equation. Okay, so if we exit out of that, now we have our linear trend line plotted to best fit to our data, and we have an equation for it. And the last thing I want to do here is show how we can use the equation of this trend line to try to estimate how many molecules of air are actually in that chamber that the experimenters used. So how do we do that? Well, going back to our ideal gas law equation, So what we've plotted here is the pressure versus 1 over volume. And, we have our equation that fits our data here. So we fit an equation that looks something like this: y equals mx, where this is a linear equation where m is the slope. And so what our slope represents here is all of this stuff, nRT. So our slope should be equal to the number of moles times the universal gas constant times the temperature. Now, as you can see, we have a slope of 971. So this 971 is equal to our N times R times temperature. So I'm going to assume that this experiment was done at a normal room temperature, which would be 20 degrees Celsius or 298 Kelvin. So, I'm going to make an assumption here that the temperature of our gas here, where all these measurements were taken, is about 298 Kelvin. So T will be equal to 298. I should be writing units here. So let me relabel this as T in Kelvin. Now, this nRT, remember, we obtained from our slope. Our slope is a rise over a run here. So the slope of our data is our pressure is the rise in pressure, over the run, which is 1 over milliliters, or inverse milliliters. So the units of our nRT here are actually going to be kilopascals divided by the run, which is inverse milliliters. So this ends up being kilopascals times milliliters. Okay. And then the universal gas constant, so let's Google what that is really quick. Universal gas constant. It's 8.31 here given in SI units. So it's 8.31 joules per degree Kelvin per mole. So let's just use so for R, we're going to have 8.31 joules per mole per Kelvin. So this will be our units for R. And so what we want to try to solve for here is, what is N? Okay. What is our number of moles? So this is what we're going to calculate. And let's go back to our scratch pad here. So what we have is this quantity, nRT. So in order to get just the number of moles, and let's see, this was equal to... Okay, so this was equal to 971. So if we want to get just the number of moles, well, we need to divide this quantity by both R and T. So our number of moles will be 971 divided by R and T. And so this will be, so that's how we're going to calculate the number of moles. Whoops, did I accidentally erase that? Okay, so our number of moles we'll be calculating as, so this was equal to 971. So this will be 971 divided by R divided by T. Okay, and that 971 had units of, let's see, kilopascals times milliliters. We're going to divide all that by the gas constant, which is 8.31. And that had joules per mole per Kelvin. times a sort of guesstimated room temperature of 298 Kelvin. So we need to do this calculation, but before we calculate all this, I want to discuss what kind of units are we going to get. So we should just end up with moles here, but is that what's going to happen? Well, we can see that the units of Kelvin down here in the universal gas constant will cancel out with the units of Kelvin here in our temperature. We'll have in the denominator here 1 over moles, so we'll end up with just moles. 1 over moles will just give us moles. But we'll still be left with a kilopascals times milliliters divided by joules. Now, so how do we deal with these units here? So I'm just going to write the units. Now, kilopascals is equal to, that means 1,000 pascals, so 10 to the 3 pascals. And milliliters, milli means 10 to the negative 3. So that'll be equal to 10 to the negative 3 liters. So if we have kilopascals times milliliters, we have a 10 to the positive 3 times 10 to the negative 3, and those are going to cancel out. So that'll just give us pascals times liters, and then we still have divided by joules down here. And the issue here, so we have one last issue here, and that is that liters is not the SI unit of volume. We want to convert these liters into meters cubed for the SI unit of volume. So let's Google really quick, what is the conversion factor between liters and meters cubed? So let's ask Google again. If you just go to Google and say, let's say liters to meters cubed, should give you a conversion factor that for every 1 liter you have 1,000th of a meter cubed, or 0.001 meters cubed. Okay, so I know this is getting a little bit messy, but that means what we need to do is, if we want to express this in SI units, whoops, where's my pen? Okay, we're going to have to change liters into 0.001 meters cubed. So after doing this calculation here, 971 divided by 8.31 and divided by 298, going to have to again divide by 1,000, or in other words multiply by 0.001. And then what we'll have is pascals times meters cubed, and that is actually equal to a joule. That is equal to a joule. Because a pascal is a force per area, right? Pressure is force per area, so that's a pascal is actually a Newton per meter squared. And then if we multiply that by meters cubed, notice we got meters cubed divided by meters squared, so we end up with Newton meters, and that is a unit of energy. That is the SI unit of joules. So once we convert this into instead of pascals times liters, we have pascals times 0.001 meters cubed. The pascals and the meters cubed equal a joule, and they will cancel out with joules, and we'll just be left with moles finally. So this is the calculation we need to do. 971 divided by 8.31 times 298. But then we can't forget to multiply by 0.001 for that unit conversion factor. And then we'll have a quantity that will just be moles. So back to our spreadsheet calculator here. Our number of moles should equal the 971, so I'll click that. Divided by the temperature and the gas constant. So make sure we're dividing by both of those by including that in parentheses. And then I need to multiply all that by 0.001 to get our total number of moles in that chamber. So remember, this is an estimate based off, we're estimating that the temperature, the actual temperature that this experiment was done in was roughly 20 degrees Celsius, which is often taken to be considered room temperature. So that's 298 Kelvin. And if that's the case, and the ideal gas law is correct, and the universal gas constant is correct, then this is how many moles were in that. In that syringe, and so we could sort of extract that from our line of best fit here, because the slope was 971, and that should represent nRT, or the number of moles times the gas constant times the temperature at which the data was taken. Again, assuming that temperature was constant. All right, and so instead of number of moles, let's change that into how many total air molecules were there. So let's do one last calculation, calculate number of air molecules. Now to go from moles to molecules, we just need to multiply by Avogadro's number. So let's just do a quick Google search of Avogadro's number. And it looks like that's 6.022 times 10 to the 23 per mole. So that is a number per mole. So 6.022 times 10 to the 23, 6.022 times 10 to the 23. So what we need to do is multiply our moles times 6.022 times 10 to the 23. Okay, and so we have a calculation for how many actual air molecules were in that syringe that the experimenters were using while they were changing the volume and recording the pressure. Okay, that'll do it for this section of the lab. In the next section, we will be exploring a non-constant temperature. So we're going to be using a constant volume chamber. So we're going to, that's a little bit easier to do, to have a chamber where the volume is constant. And assume it is sealed, so no air molecules are getting in or out. And we'll change the temperature to see how the temperature, and then we'll also be recording the pressure. So we'll be keeping the volume constant, changing the temperature, and recording the pressure to see what the pressure versus temperature relationship is for a gas. See if it is as predicted by the ideal gas law. And then we can even use our data to measure what absolute zero is. So that'll be in the next section. Okay, so I'm going to try to keep this all contained to one YouTube video. So what I'm going to ask you to do is actually pause the video here and then watch the second video linked that will show you an experimenter taking a constant volume chamber, changing the temperature of that chamber, and recording both the temperature and the pressure as the temperature changes. So go ahead and watch that video now, and so pause this one and watch that video, and then we'll get started on the analysis for the measurements taken in that video. Okay, so after watching that second video, you should have an idea of what we're doing in part 2 of this lab. I'm going to go ahead and label this part of the spreadsheet part 1. And then I'm going to scroll down a little bit, give a couple blank lines, and then call this one part 2. Now in part 2, what we're doing is taking a gas sample, measuring its temperature in Celsius, and its pressure. So I'm making my columns here, so go ahead and follow along and make these columns. The pressure again in kilopascals. Now, in that video, only 3 data points were taken. So, if you wanted to, confirm the ideal gas law relationships a little better, you should probably take more data points. And if you wanted to get a better measurement of absolute zero, like we're going to do here, again, you should probably get more data points. But at least with this, you can see how this type of experiment is done. So I'm going to copy in the 3 data points we're using. the lowest temperature was 1.4 degrees Celsius, and at that temperature, a pressure of 92 kilopascals was recorded. The second lowest temperature was 26 degrees Celsius, and there 102 kilopascals was recorded. And the highest temperature was 40.3 degrees Celsius, and there a pressure of 107 kilopascals was recorded. Okay, so let's go to our ideal gas law equation again. Okay, so P times V, pressure times volume, should equal the number of moles of gas times the universal gas constant times the temperature. This time we're assuming the volume to be constant. Well, we're in a constant volume chamber. No gas is leaking in or out. So if we solve for pressure, we get N times R divided by V times T. Okay, and I'm going to kind of group these together. We're assuming all this is constant. The number of moles would be constant, assuming no gas is leaking in or out of the chamber. R is in fact a constant. And the volume of the chamber is constant. So the type of relationship we should see here is one like this, y equals mx, with no y-intercept. Although we will see a y-intercept because, remember, the ideal gas law assumes that you're using a temperature in Kelvin, or an absolute, in some sort of absolute temperature scale. But we are not using an absolute temperature. We're using Celsius. So Celsius, in Celsius you can go negative, and that's why we will see. We're actually going to see a y-intercept here. So we'll have a y equals mx plus b, rather than just y equals mx here, as this equation looks like. So let's go ahead and make our plot, and let's see if it's a linear relationship. Although, really, if we really wanted to test, if it's truly a linear relationship, we should have more than just 3 points. But I guess technically 3 works to see if they all fall on a line. Okay, so let's make our plots of pressure versus temperature. Again, go up into Inserts, Chart. I'm going to try to make this smaller. Get it out of my way here. Okay, and then under data range, delete this, click this button, and select your pressures. So your pressure column, click OK. Oh, whoops, actually that's not what I want. I want temperature to be on the y-axis, and that why that is, I'll explain in a moment. So again, go back into data range and click this button again and delete that, and choose your temperatures. Okay, and then go to your x-axis, click on that, choose this button for selected data range, and click in there and do your pressures. So we'll have temperature on the y-axis, pressures on the x-axis. Oh, and I forgot to change this into a scatter plot. So hopefully it fixes that. Looks like it did. Okay, and now if we scroll down, again, how do I fit a line to this? Well, I'm just going to exit out of this and double click on the data, scroll down a little bit, and choose trend line. Make sure that's checked. Make sure it's linear. Under label, select use equation. And we have our equation here. Okay, so exit out of that. And so I want to talk about what this equation represents and what our data is kind of showing here. First of all, what we're seeing is that as you increase the temperature, so as you go up on the y-axis, the pressure increases. So that's part of what the ideal gas law says. You increase the temperature, then the pressure should increase. And we are seeing that. As you go up in temperature, you go up in pressure. Now, what does this y-intercept represent? So if we were to assume that this that our if we were to take more data points, maybe for higher and higher temperatures or lower and lower temperatures, you could keep going below zero. Let's assume that this trend were to continue to be followed. And then you could ask yourself the question, well, at what temperature would the pressure reach zero? So if this trend line were to keep, going, if we were to keep lowering the temperature and recording more and more data, would it be possible to reach a temperature where the pressure inside the chamber would reach a zero? And that's what this y-intercept represents here. That's where this line crosses the y-intercept. So at the y-intercept, the x-axis is 0, and the x-axis represents pressure here. So that is where the pressure would reach 0 pressure, and where that happens would be the temperature. So we're seeing that a temperature of negative 236 degrees Celsius, if this behavior were to continue, would be the point where we would reach 0 pressure. And could you go below 0 pressure? Well, again, I don't know how that would make any sense. How could the gas molecules exert less than 0 pressure on the walls of their container? And so what this represents is a measurement of absolute zero, to be negative 236 degrees Celsius. Now let's see how accurate this measurement is. Let's Google absolute zero in Celsius. Let's see what we get. Why isn't it showing up? Oh, yes. So it's actually minus 273 degrees Celsius. So we're not getting the most accurate reading, but this was a pretty simple experiment. Done with only 3 data points. So probably, if we took more data points, we'd get a slightly more accurate value. But the currently accepted value of absolute zero relative to the Celsius temperature scale is actually negative 273 degrees Celsius. But anyways, that's the last thing I wanted to do in this lab. So let's just label this our measurement for absolute zero. And that'll do it for this lab. All we got to do now is submit our spreadsheet. So to submit this spreadsheet, make sure yours is titled with your name. Click up on the share button. So in the top right, you should see a share button. So click that. And right here, click on change to anyone with the link. So make sure you click that. So anyone with the link can view it. That means I'll be able to view it when you submit it. So hit got it. Then hit copy link. And with the link copied, now we want to go up into Blackboard. Alright, once you're on the Blackboard homepage, you should see a tab called Labs now under Course Modules. If you click on that, you should see Lab 1, Gas Laws, and Absolute Zero. Click on that, and yours might look a little bit different by the time this is up, but what you should see is a link called Lab 1 Submit. Click on that link. Under Assignment Submission, click on Write Submission, and then just paste the link to your spreadsheet. So make sure you paste the link to your spreadsheet with the, with the correct settings so that I can view it. Then just hit Submit. And that should be it. You should be done. And so once I see your spreadsheet, I'll be able to grade it and give you some points for it. Okay, that'll do it for our first lab of the semester. Please let me know if you have any questions.